Dear students, in this class we will be discussing three base catalyzed rearrangements, namely Favourski rearrangement, benzilic acid rearrangement and Dakin reaction. So first one is the Favourski rearrangement. It was discovered by the Russian chemist Favourski, and it involves the reaction of alpha haloketone. This is a keto group, and in the alpha position there will be a halogen. So alpha haloketones on treatment with a strong base, it can either be sodium hydroxide or any hydroxide or an alkoxide. Then these alpha haloketones undergo rearrangement to form carboxylic acid or its derivatives via a cyclopropanone derivative, cyclopropanone intermediate. So I hope the statement of Favourski rearrangement is clear to you. It involves the base catalyzed rearrangement of alpha haloketones to a carboxylic acid or its derivative via a cyclopropanone intermediate. Now, let us go through the mechanism of the reaction. This is the mechanism as given in PS Calci, organic reactions and their mechanism. So, this is alpha haloketone. This is the keto group, and there are two alpha carbon atoms here. One contain a halogen and the other contain a hydrogen. So in the presence of a strong base, the alpha hydrogen is subtracted to give a carbanion. The carbanion then undergoes cyclization with the elimination of Cl- to form cyclopropanone intermediate. The cyclopropanone intermediate is then attacked by the base at the electron deficient carbonyl carbon. Then we will get another intermediate 3. Now, the next step involves opening of the cyclopropanone intermediate. It can open in two ways, either in this manner or in this manner. And the most stable of the two carbanion is formed. So the opening occurs in such a way that the carbanion formed will be the most stable. In the next step, this will abstract a proton from the base to form the carboxylic acid derivative. Now let us look at the mechanism with our substrate. This is the alpha hydrogen. It is abstracted by the OH group and a carbanion is formed or an enolate is formed. And then this enolates undergoes cyclization to form the cyclopropanone derivative. The third step is the opening of the cyclopropanone derivative by the base, and this opening can take place in two ways, and the most stable carbanion is formed. Next step is the proton transfer to form the carboxylic acid derivative in this case. The direction of ring opening of cyclopropanone is determined by the most stable carbanion. That is, in both the cases, these are two different alpha chloroketone. In both the cases, if you write down the mechanism, we will get this cyclopropanone derivative, and it opens in such a manner as to obtain the most stable carbanion. So, in both these cases, even though the substrates are different, the final product will be the same because it goes through the most stable carbanion. One of the most important points in Favourski rearrangement which you have to remember is in the case of cyclic alpha haloketone. Here this is cyclohexanone. At the alpha position you have a chlorine. So in the case of cyclic alpha haloketone, the rearrangement is often followed by ring contraction. So you will get a carboxylic acid derivatives which is ring contracted. This is a cyclopentanone derivative. Again we will get an ester which is a cyclobutane derivative. So here the mechanism is as follows. First is the abstraction of alpha hydrogen to form the carbanion. The carbanion then forms the enolate. The enolate undergoes cyclization to form cyclopropanone derivative. This is followed by the ring opening to give another carbanion, and which is followed by addition of a proton to form the ring contracted carboxylic acid. So that was all about Favourski rearrangement. The next one is Dakin reaction or Dakin oxidation. This reaction is named after the British chemist Henry Drysdale Dakin, and it is very closely related to Baeyer-Villiger oxidation, which you might have already studied during your course. So Dakin reaction is a redox reaction which is used to convert ortho or para-hydroxylated phenylaldehyde or ketone. It can be an aromatic aldehyde or a ketone, but it should contain a ortho or para-hydroxyl group. After oxidation, the product obtained is a benzene diol. Benzene diol in this manner, and the reagent is alkaline hydrogen peroxide. So Dakin reaction is a redox reaction which is used to convert an ortho or para-hydroxylated aromatic aldehyde or ketone to a benzene diol with alkaline hydrogen peroxide. Side product will always be an carboxylic acid. Coming to the mechanism, the first step is the nucleophilic attack of the hydroperoxide anion at the electron deficient carbonyl carbon to form a tetrahedral intermediate in this manner. In the second step, the aryl group migrates from the carbon to oxygen. This group migrates from this carbon to this oxygen. OH group is eliminated. So we will get a compound like this. The third step is the nucleophilic addition of hydroxide ion to the ester carbonyl, attack at the ester carbonyl to form another tetrahedral intermediate. Now this is an unstable intermediate. It collapses to eliminate the phenoxide ion. Now this double bond, this negative charge comes between C and O, and we'll get a stable molecule. This cleavage of the CO bond to phenoxide ion. Formic acid is eliminated. Then it abstracts a proton from formic acid to give the benzene diol. So this is the mechanism, a fairly straightforward mechanism. Now coming to the third rearrangement, benzilic acid rearrangement. This is a very important organic reaction which is used to convert 1,2-diketone, especially aromatic 1,2-diketone. If we have 1,2-diketone means two carbonyl groups at the adjacent to each other, and if it is flanked by two benzene ring, then the compound is known as benzil. And if it is flanked by two furans, the compound is known as furyl. So these diketones are converted to a 2-hydroxycarboxylic acid using a base like KOH or NaOH, and the resulting intermediate is subjected to an acid workup. So in this case, benzil react to give this 2-hydroxycarboxylic acid, which is called benzilic acid. So this reaction works well with aromatic 1,2-diketone, but it fares poorly with aliphatic 1,2-diketone. Similarly, in the case of furyl, we will get the carboxylate, potassium carboxylate in intermediate, which on treatment with acid will give furylic acid, which is another 2-hydroxycarboxylic acid. It has a fairly simple mechanism. In the first step, hydroxide ion attack one of the electron deficient carbonyl carbon. So we will get a tetrahedral intermediate. In the next step, the phenyl group migrates from this carbon to this carbon, and the negative charge comes to between here. So we will get OH, C double bond O, CO minus, again the phenyl group. So this is our intermediate. Here we have a alkoxide ion and carboxylic acid. Then there will be a proton transfer. This H will be transferred from the carboxylic acid to this alkoxide ion. So we'll get a carboxylate anion. Step 4, the acid workup, and gives the protonation of this O to give the desired product. So we will get a benzilic acid. So these are the 3 base catalyzed rearrangement, which are fairly related to each other and fairly simple. Please go through the reactions. If you have any doubt, please contact me directly.